So hello, today I'm going to talk about the restriction theory for hyperbolic paraboloids, and everything I'm presenting is joint work with Marina Iliopoulou from the University of Kent. So to begin, throughout this talk, we'll let Q denote some non-degenerate quadratic form acting on n-1 variables. To this function, we'll associate a hypersurface, HQ, which is given by the graph of Q over a bounded region in the parameterization domain. So in particular, we're taking the graph of Q over this ball in n-1 dimensions of radius 1 centered at the origin. So with this hypersurface, we can associate an extension operator in the usual manner. So this is an operator EQ, which is going to take some f, which lies on the parameterization domain, and extends it to a function on the ambient n-dimensional Euclidean space. So how does it do that? So if we plug in a vector x, we're going to integrate f against this oscillatory factor, and we have a phase in the oscillatory factor given by the inner product of our input vector x with the graphing function of this quadratic form, so the parameterizing function of our hypersurface. So of course, this is a meeting all about restriction theory and these extension operators, so I'm not going to spend any time motivating this definition. We'll take it for granted that this is an interesting operator to study. And the fundamental question is to understand its LP mapping properties. It's well known that the curvature of the underlying hypersurface plays a significant role in restriction theory. And in this instance, our hypersurfaces have non-vanishing Gaussian curvature. So from the restriction theory perspective, they're part of the best possible case. Okay, they have the best possible curvature properties. However, when one starts to delve into more subtle aspects of the theory of these operators, it becomes apparent that the Gaussian curvature alone is insufficient to fully understand these operators. And in particular, we'll also use information about the principal curvatures, and in particular, the signs of the principal curvatures will be important in our study. In light of this, I'm going to define sigma to be the quantity which I'll refer to as the signature of the quadratic form Q, and that's just the difference between the number of positive and the number of negative eigenvalues of this quadratic form. So geometrically, this is the difference between the number of positive and the number of negative principal curvatures of this hypersurface at every single point. Okay, so with these definitions, the main problem is to establish the following range of LP estimates for our extension operators. So in particular, whenever P is strictly bigger than this magic exponent 2n over n-1, we expect LP to LP boundedness. So I'll remark that the range of exponents here does not depend on our choice of non-degenerate quadratic form, and this is due to the fact that they all result in hypersurfaces of non-vanishing Gaussian curvature. So in particular, the signature does not play any role in the range of exponents in the conjecture. Of course, the choice of expanded quadratic form will manifest itself in the constant in the inequality. The main result I want to present today is joint work with Marina Iliopoulou, which proves this conjecture for a restricted range of P, so quite a heavily restricted range of P. In particular, we have this LP boundedness for some number which is bigger than 2n over n-1, and it's given by this slightly complicated looking formula. So you'll note our result, in contrast with the conjecture, depends on the signature of the quadratic form, and it also depends on the parity of the dimension, although the two things are related. So this looks a little bit strange and unnatural at first sight. So in order to contextualize the result, I would like to remark that we actually prove inequalities for a more general class of oscillatory integral operators. These oscillatory integral operators are variable coefficient generalizations of these EQ. And it turns out at that level of generality, our theorem is in fact sharp. So what I mean by that is that you can find examples of operators which satisfy some variable coefficient analog of the signature condition for which this range of LP boundedness is best possible. So in that sense, the exponents in our theorem are a natural barrier for this problem. In particular, if you wanted to prove LP bounds for these extension operators below our range, then you would have to use properties of these operators which distinguish them from the general class of variable coefficient operators. I'd like to remark that there was some interesting work of Alex Barron last year who proved a range of LP bounds for exactly these operators, which is somewhat more restrictive than our result. However, I think this is quite a nice little argument because it's based around bilinear methods, whereas our arguments are all based around multilinear theory. So Alex Barron's work kind of complements ours in a nice way, and it'd be interesting to see if the two approaches can be hybridized. So I want to try and explain why we see this signature cropping up in our results and to give a sense of why it's an essential feature of this problem. Now, as I just mentioned, our approach is based on multilinear theory of these extension operators. And in the multilinear setting, we see that the signature really does play some role. In order to describe the multilinear setup, we first have to make a standard definition. So here I'm going to fix k subsets of our parameterization domain. So that's k sets u1 up to uk. They're all lying in this n-1 dimensional ball. Now, for every set uj, we're going to pick some arbitrary vector omega j lying in uj. So this omega j lies in the parameterization domain. So it has some point in the hypersurface lying above it. You can see that in the picture. And for that point in the hypersurface, we can look at the normal vector to the hypersurface. So that's denoted by this g omega j. G is the Gauss map. Now, we'll say that the sets u1 up to uk are nu transverse if whenever you pick such a k-tuple of points omega j, and we form the k-tuple of normal vectors g omega j, then these vectors are quantitatively linearly independent. More precisely, if we form the k-fold wedge product of these normal vectors g omega j, as you can see in the slide, then the norm of this k-fold wedge product is bounded below by this parameter nu, which is some positive number. So we can see this in the picture if we look at the three blue arrows corresponding to well-separated normals on our kind of saddle surface. They span the whole three-dimensional Euclidean space. So with this geometric definition, we can describe the multilinear setup. So here I'm going to state an L2-based multilinear version of the extension conjecture for these quadratic hypersurfaces. Suppose we have a k-tuple of functions defined on our parameterization domain that satisfy the following transversality condition. So each function fj is supported in some set uj, and these uj sets form a transverse family. So they're nu transverse with some parameter nu, which is about unit scale, say nu equals 1 over 100, or 1 over 100n. So with this setup, we have an L2 to LP multilinear inequality for the range of p as stated. So of course, this expression for the p exponent is somewhat complicated, so I'll come back to this later. So what this multilinear inequality says is, if we take each of these fj, we plug them into our extension operator, we take absolute values, we form the geometric mean of these k functions, we measure that in LP, we can bound that by the geometric mean of the L2 norms of the fj's. Okay, so this is the standard multilinear setup when you're working with these kind of k restriction problems. As I mentioned, we have rather a complicated exponent appearing in this conjecture. At the moment, I just want to highlight that it, of course, depends on n and k, the ambient dimension and the degree of multilinearity. but it also depends on sigma, which is the signature of the quadratic form. And so in contrast with the linear theory and the multilinear setup, the signature plays an essential role in the sense that it appears in the range of estimates that we're shooting for. So let's forget about the exact value of this exponent for now and just make some comments. So first of all, this range of P is necessary. And again, this shows that the signature is playing an essential role. And the necessity comes from an example due to Ana Vargas. So the Vargas example was for the two-dimensional hyperbolic paraboloid in R3, but it can be extended and concatenated in various ways to show the necessity in this full generality. To prove our main theorem, we actually established a weak version of this conjecture, and in particular we used the formalism of broad estimates, which was introduced by Larry Guth. And indeed, our methods of proof were heavily influenced by Guth's work and involved his celebrated polynomial partitioning scheme. So I don't really want to get into any of the details of the proof of our main theorem or what these broad estimates entail, but I do want to try and describe a little about the numerology in the problem, why we see the sigma cropping up, and how sigma plays a role in these problems. So let's go back to the exponents featured in the conjecture. So of course, there are three distinct regimes depending on the degree of multilinearity k. So first of all, if k is small, it's close to 1, then we get the exponent 2n plus 1 over n minus 1. And I'm sure everyone will recognize this as the Stein-Thomas exponent in the L2 restriction theorem. In particular, this multilinear estimate follows from Stein-Thomas using Held's inequality. So there's no real multilinear feature to this inequality. It's just a direct consequence of the linear inequality. In the other extreme, if k is close to n, then we get the exponent 2 times k over k minus 1. And you may recognize this as the k-linear exponent in the celebrated Bennett-Carberry-Tau multilinear restriction theorem. So in this case, we also get the sharp range of multilinear estimates for free, this time coming from the Bennett-Carberry-Tau work. So really, the only new feature of this conjecture is understanding what happens when k is close to half the ambient dimension in this middle regime. And that's where we get estimates that improve over Stein-Thomas or Bennett-Carberry-Tau. Now, I want to reflect on some features of the inequalities we're using in these extreme regimes. So first of all, remember, Stein-Thomas only uses the curvature of the underlying hypersurface, this hyperbolic paraboloid. And we do not use the transversality hypothesis in the multilinear setup. And this is obvious because we can prove the inequality via Stein-Thomas and Held's inequality. So if we apply Held's inequality, we isolate each of the factors in the geometric mean and we treat them individually. We don't use any of the transversality properties which describe how the terms in the factors relate to one another. At the other end of the scale, the Bennett-Carberry-Tau theorem only uses transversality and it doesn't see the curvature of these hyperbolic paraboloids. Now, in the middle regime, we beat the estimates obtained from Stein-Thomas and also the estimates obtained from Bennett-Carberry-Tau, and therefore we necessarily have to use both the features of this multilinear setup. We have to use the transversality in our hypotheses, and we have to use the curvature of the hyperbolic paraboloids. And it's in this interplay between these two geometric features of the problem which make the new regime somewhat subtle. Okay, so why do we see the signature appearing in these estimates? Well, that's a little bit of a complicated question, and it has more than one answer. But I want to highlight the role of a signature in just one aspect of the analysis. So that's the wave packet decomposition, which I'm sure many of you are familiar with. So my plan is to finish off this mini lecture by briefly reviewing the wave packet decomposition and highlighting one feature of this tool, which relates to the signature of the underlying quadratic form. So the first step towards performing the wave packet decomposition is to introduce a spatial localization to the problem. So in particular, I'm going to choose some big scale R, and we're going to localize our operator in the spatial domain to some ball BR of radius R. So you can see this in the expression on the right here. We've taken our extension operator and we've simply multiplied it by a cutoff to this ball BR. And you should think of this as a smooth cutoff. So some bump function supported on that ball, for instance. Now, if we localize in the spatial domain, that should have consequences for how the operator looks in the frequency domain due to the uncertainty principle. So in particular, localizing to scale R in the spatial domain corresponds to inducing uncertainty at the reciprocal scale 1 over R in the frequency domain. So let's try to understand what that means in practice. So let's go back to our global operator. So we have the extension operator EQF here on the left-hand side, and let's look at its Fourier transform. Let's see how it behaves in the frequency domain. Well, this Fourier transform is not terribly nice. It's a singular measure which is supported on our hypersurface. So this little ball is representing our hypersurface HQ in this instance. And however, once we introduce the spatial localization on the right-hand side, in the frequency domain, we get this reciprocal R uncertainty. And the effect of this is that the Fourier transform is now a smooth function, which is supported on a fattened up version of the hyperbolic paraboloid. So it's supported on a 1 over R neighborhood of our hypersurface. So by introducing this spatial localization at scale R, we resolve the singularity in the frequency domain to scale 1 over R. Okay, so the next step is to take this fattened up frequency support and to perform a partition of unity, breaking it up into little rectangular pieces. So you can see this in the figure. In particular, we're going to cover the 1 over R neighborhood of the hypersurface with these little rectangles, which I'll refer to as slabs. So each slab has n-1 long directions, and these correspond to the tangent directions to the hypersurface at the center of the slab. And the long directions all have size reciprocal square root of R. They have a short direction, which is the remaining direction, which is normal to the hypersurface at the center of the slab. And this short direction has scale reciprocal of R, so it corresponds to the width of the neighborhood. Now, the reciprocal square root of R scale is chosen so that these little rectangles fit neatly around this hypersurface. And in particular, at this scale, we don't really see the curvature of the hypersurface when we look at this localized piece on this slab. So we perform this frequency decomposition of our operator according to this slab decomposition, and each of the frequency localized pieces are written as f sub theta, where theta corresponds to a choice of slab. I now want to understand what these f thetas look like on the spatial domain. So in the frequency domain, they're simple to understand because by definition, they're the frequency localization of our extension operator. What do they look like on the spatial side? Well, we can guess what the picture should be using the uncertainty principle. So temporarily, I want you to suppose that our slab is centered at the origin. So we have this little rectangular box, it's the red box in the picture. and this contains the frequency support of f sub theta. Now, what the uncertainty principle tells us is that in the spatial domain, f theta should be essentially constant on translates of the dual slab. And we'll refer to these translates of the dual slab as tubes. So they look like cylinders, which have length r and point in the direction of the normal to the slab. And they have width square root of r. So the scales are given by the reciprocals of the scales of the frequency slab. Okay, so we can think of f sub theta now as a weighted sum of characteristic functions of these tubes. However, this is all under the assumption that the slab is centered at the origin, whereas in fact it will be centered away from the origin, typically on some piece of the hypersurface. So as we translate the slab away from the origin, what happens on the spatial side is that we pick up some oscillation. So each of these tubes is carrying some oscillation. It's actually with a uniform choice of frequency. So that's what these wiggly lines denote. And what is that frequency? Well, it corresponds to the vector given by, say, the center of our slab. That's the xc theta in the picture. So these tubes are all oscillating with frequency xc theta. So these observations lead to this wave packet decomposition. So we first decompose our operator, localized operator and frequency to form the f thetas as before. And then we now decompose each f theta in the spatial domain. And this is so that to form these functions f theta v, where f theta v is just some localization to one of these parallel tubes. So the v corresponds. As you vary over v, you move around over these different translates. So from our observations, we've seen that the f theta v has frequency given by the center of the frequency slab, which is this xc theta, and the f theta v's have spatial support inside these tubes, and each tube has direction given by the normal to the slab, which is the normal vector to the surface at the center of the slab. So here I've given an example where we have the elliptic paraboloid, and we have a choice of slab, a choice of xc theta, and the corresponding normal direction. So the important thing to bear in mind here, and this is why I've highlighted some of the text in red, is that there is a relationship between the frequency xc theta and the direction of the tube. In particular, we know that the Gauss map is an injective function. So from this, we see that the frequency dictates the direction and vice versa. There's a one-to-one correspondence between the frequency of the tube and the direction of the tube. And we can see this very easily in our example, because once we fix the frequency, we fix this omega theta, and then that clearly dictates the direction of the tube and vice versa. Okay, so there's this nice relationship between frequency and direction. Now, this is a key feature of this restriction problem, and so I want to see how it plays out in a particular setup. So one interesting case to consider is where our wave packets form some kind of configuration. So for instance, we can consider the case where the wave packets are aligned near some submanifolds. And this is what I've drawn in this picture. We have a collection of wave packets that are all aligned along some hyperplane V. Now, this alignment constrains the directions of the wave packets. So the directions must lie in some great circle in the sphere. And because we constrain the directions, and the directions and the frequencies are in some one-to-one correspondence, the frequencies must also be constrained. So let's look at what the frequency support looks like in two different cases. So first of all, I'm going to look at the elliptic case, where our underlying surface is an elliptic paraboloid. Well, in this picture, if we draw all the points on the paraboloid whose normals point in the directions of these tubes, then these points lie along a slice of the paraboloid, which is in fact obtained by the same plane V. Okay, so there's this nice simple relationship between the directions and the frequencies. And in particular, the frequency support of the operator here is going to lie along some narrow neighborhood of this plane V. And this is essentially always the case in the elliptic setup. We have some frequency support which is in some sense close to a slice formed by this plane V. Now let's contrast this with the hyperbolic setup. So here I'm taking a hyperbolic paraboloid and I've drawn the same slice formed by the plane V. However, when we draw the points on the hyperbolic paraboloid with normal directions parallel to the tubes, we see they lie along a subspace which is perpendicular to V. So we have a completely different kind of phenomenon occurring in the hyperbolic case. So this interplay between the frequency of the wave packets and the directions of the wave packets, and the fact that the relationship is somewhat different in the hyperbolic compared to the elliptic case, is one feature of the hyperbolic problem which distinguishes it and leads to these different multilinear theory for these operators. So of course, this is avoiding any details of why this should cause the operator to satisfy different LP bounded bounds, but that's a discussion for a longer talk. So thanks very much for listening, and thanks to the organizers for putting on this event. It's great to experiment with this new online format and to get everyone in the community together. So take care, all the best, stay safe, bye-bye.